afternoon, everybody. Welcome to the Art of Reverse Engineering Flash Exploits. You are in the Jasmine Ballroom, and your speaker today is Matt O. Before we begin, a few brief notes. Stop by the business hall located in Bayside AB if you haven't done that already. The Black Hat Arsenal is on the Palm Foyer on level 3, and of course the Arsenal reception at 1700. If you haven't picked up your merchandise today, today is your last chance to visit the Black Hat Schwagen bookstore, and I believe it closes at 6. And also, please visit the Kali Linux Lab in the Mandalay Bay A, and please put your phone on vibrate so that it does not interrupt the presentation. And if you look around you, there are 3 microphones available. At the end, there'll be a Q&A, so if you could please find the microphone nearest to you and step up so that we can all hear your question. We really appreciate it. And now here's Matt.
Yeah, thank you. So agenda. So we are going to talk about the reverse engineering method for the Flash exploit today, actually. So first, we will look into the method that we used and we found some effective. And next, we are going to the real examples from last few months or maybe few years. And we will look into some RW primitives that are popular for Adobe Flash exploit. And we will talk about some CFG technique, actually, to break these exploits. It's a kind of attempt from us or from the industry. And we will talk about other technologies from the attacker side, how they are trying to work around these new mitigations. And that will be it. And the thing is that Adobe Flash Player exploits or vulnerabilities it was not so popular before 2013, right? 1 or 2 years, actually it was the era of actually Java exploits, because Java exploits are usually they work 100% because they are usually logic bugs or vulnerabilities. So it was in fashion, but somehow Oracle fixed it by just introducing click to play. So it just killed all those exploit scene actually. And browser got more secure because of all those CFG and isolated heap and all those mitigations. So those targets became more non-attractive to the attackers. That's when this new Adobe Flash Player exploit came again. And especially after 2013, there was a Lady Boyle exploit which introduced the vector corruption method. And this one used for 2 years. So every exploit since then until mid 2015 or something, then they were using this method. Very, very effective way to exploit Flash vulnerabilities. But in 2015, Adobe did a lot of effort to introduce new mitigations, and vector corruption mitigation is one of them. And after that, they introduced CFG, and it broke a lot of exploit methods after that. And first, let's talk about how we can reverse Flash exploit. So first, the obvious choice is actually the compilers, right? So there are a lot of the compilers out there. But I just used a lot of them, but I just found that these 2 are just good. And the first one is JPEG's free Flash decompiler. This one is open source and free. It works very well. The only problem is that it renders the Flash every time it loads it. So you should not open the malicious Flash file from your host machine. You should run it from your virtual machine or something, because actually the exploit can run if you just open it from this tool. The second one is ActionScript Viewer, which is commercial. So this one really works well. But the thing is that I will talk about some limitation with decompiling, because if the compiler works 100%, there is nothing to worry, right? So if you just decompile the exploit, and maybe you can put whatever code you want there, and recompile it and just run it again. Then in that way, you can debug the exploit very well, very easily, but in reality, it doesn't work like that. One of the reasons is that they are doing a lot of obfuscations, and out of all those obfuscations, the most advanced one I found is actually the broken code shown here. So if you open some like a recent Angular exploit, one of those, then you probably will see these lines, like the red lines there, like a go-to statement or unresolved jump statement. Actually, they are broken decompiled code, so you can't recompile it, right? And if you actually open the file from disassembler, not decompiler, then actually you can see that there are some garbage code, and actually there is one garbage basic block itself. The code on the bottom, the label 503 will never be called. So in that way, they just put a bunch of garbage code there, and they will confuse the decompilers. So decompiler is not perfect, and the problem is that the fundamental problem in the decompiler is that when you decompile something, you will never be 100% sure that that is the original code that generated the the sweep file or the ABC record. So that's why you should use disassemblers. And one of those disassemblers, Rhapsody, is open source, and it's very powerful. And I found it really useful. But the only problem is that you need to understand the ABM instructions. And there is a good reference from Adobe here. I put a link there, and maybe you can find it later. And still, disassemblers can be broken. So something like a lookup switch, this one is also found from Angular, actually. So it has a lookup switch instruction there, and it has label 6 to some big number, 42976. So actually, it will go out of bounds of the file itself, the ABC record itself. So the Rhapsody will fail, and it will just spit out some exceptions. But you can just actually just patch the Rhapsody because it's open source, and you can just limit the length of the lookup switch and to small numbers, and you can just skip those like invalid lookup switch statement. So that is one way you can actually reverse engineer Flash exploits. And the other approach we did is actually it originates back from 2012. I presented at StreamCon about some bytecode level instrumentation, and I did some open source project as a Flash hacker. And we internalized the tool at Microsoft, and we made more advanced filtering options, more advanced instrumentation options. But basically, the Flash hacker open source project has the basic like a framework of what you can do with bytecode instrumentation. The only problem with bytecode level instrumentation is that when the exploit uses some heap spraying or some CPU intensive or memory intensive code run, then it will actually, our like instrumented code will intervene with all those like exploit itself and will make the exploit fail. But the thing is that if you use it carefully, not like instrumenting those like CPU intensive or memory intensive code, you just filter them out. And in that case, it's kind of very useful tool for RCA, root cause analysis, or mitigation bypass research. So I will show you the real world example that we use this tool from the slide after. And the other very helpful tool to its resource is actually ABM Plus source code. So if you go, it's on GitHub, and if you go there, so Adobe kindly actually shared their ABM Plus ABM machine, virtual machine source code on GitHub, and actually it's kind of 2 or 3 years old, but a lot of like internal structures are there, and it can be a really good reference for you when you are actually reverse engineering exploits. And you can also do some native level debugging of the Flash, but it's really challenging because the Flash file itself is like more than 10 megabytes, and when it's in the debugging, like in the process memory, if you don't have any symbols, it's not easy to figure out what function is what function is doing what. So let's talk about RW primitives first. So from the agenda, this is second part. And we will talk about three different RW primitives. And first one is a vector length corruption. This one I mentioned already, but let's talk about RW primitives first, right? So RW primitives are the objects or functions the exploits are using to achieve memory read and write. So the thing is that before ASLR and DEP, actually a lot of like exploits didn't need these RW primitives or something. They are just corrupting something, some adjacent object, or they already know some address, some fixed address, and they just jump there. That kind of technique worked. But after ASLR, DEP, ASLR and DEP were introduced, you need full RW primitives to achieve RCE. So RW primitive doesn't mean you get the RCE. So even though you have full read and write privilege on your target process, you still can fail to achieve RCE. So that's the old theme here, actually, how we are blocking the execution of code even though they have RW primitives, and how the attackers are actually workarounding those. And from defender's point of view, actually knowing the RW primitives for Flash exploits is very important, because if you know that and if you track those operations actually, then you can figure out what technique they are using to circumvent CFG or other mitigations. So first, vector length corruption, this one came from like 2013, and it was used like kind of 2 years. It's long time. And Adobe finally fixed it last year, and Adobe blogged about it, and GPG actually blogged about it too. And you can find a very detailed explanation from those resources. And we are going to just go into just one example from the most recent one, 2015 5122. This one is used after free vulnerability actually. But first, it's just doing some vector spray. But the vector spray is not really huge, like 1 giga or 2 gigabytes of vector. It's not that kind of big vector spray. It's just how many? Just like a few megabytes, at most a few megabytes. And they are doing another vector spray, and they make some holes in between. And they are just spraying some vulnerable object in between and trigger the use after free. So for the detailed explanation about this vulnerability, you can find a lot of resources. Just search for the CB number. You can find a lot of helpful resources from the internet, actually. And just trigger the use after free bug, and actually it will, the adjacent vector element is corrupted, and it will be using that to corrupt the other vector element to a big length here. So the yellow background lines are actually showing those code. And these exploits are, the exploit is kind of really typical like a vector corruption. And if you use instrumentation technique, then actually you can see how this vector length corruption is happening. And because you can just instrument a vector object, right? So if you just instrument those, and you can check the length whenever the object is accessed, then if the length becomes more than what was designated initialized in the first place, then you know that the vector is corrupted. In this case, it's corrupted to 4,000, 1,000, it's big number. And the exploit will use this RW primitive to access the other internal object inside the process. So next RW primitive that we are talking is actually byte length corruption. So after Adobe fixed vector length corruption, the bad guys actually moved to byte length corruption as expected actually. So this one is CB 2015 A651 example, which was used for Domnium campaign, which shares the same IOC as, the Dark Hotel, as known from Kaspersky. So from this exploit, actually, they are using the vulnerability is kind of very impactful actually in this case, because the SI32 is the instruction actually that can directly access native memory. But in this case, there was some boundary check error, and it could access whatever memory it wanted, right? So in this case, it will just directly modify adjacent byte length field memory location to some big number here, and after that, it will just search for some corrupted byte element, and it will just use it as a RWM primitives. So in this case, the exploit is very well written, and it's kind of modularized very well. So read 32x86, it will be reading whatever memory. You just pass the address, it will just read whatever memory from the process. The second one is write 32x86. This method will, you just put whatever address and value, it will override whatever value from the process. So the next one is actually kind of tricky one. The convolution filter matrix to tap stops type confusion. We just saw this once, and it is using this specific matrix array, and it will induce the confusion. The confusion process is kind of very, very complicated actually. It's not easy to understand here. But when it reads it actually, you just pass some address to convolution filter object, and you can read out the actual memory from text format tap stops element 0 from the yellow background line actually there. So looks like the convolution filter matrix will like override some address field from the internal structure, and it will make the reading of the any process memory possible. The point is that even though they have these other kind of the RWM primitives available, eventually they use this RWM primitive to achieve byte array RWM primitives. The attackers prefer using byte array RWM primitives. So they are actually change this RWM primitive to convert this to byte array RWM primitives later, so that they can work more conveniently and more stable in more stable way. So we talked about the RWM primitives. So getting RWM primitives are kind of easier than actually executing something, because even though you have access to the process memory, there are a lot of like hurdles until you get actually code execution. Because one of those mitigation is the most recent one is actually CFG. So what is CFG? So you can define it in a very different way, but you can just open up some recent Windows binaries, and you will see probably see these lines like it got check equal far pointer here. So it will actually do some whitelisting upon what target process memory it can jump or call. Then it has some bin masks set up somewhere, and it will just filter out whenever some wrong jump is happening here, right? So if you define it in more formal way, actually, actually I didn't define it here, but CFG can be very powerful in actually making the cost of the exploit development very higher. Actually, the thing is that the technique here looks very simple. Actually, it's just whitelisting, but actually for last 2 years, no zero-day exploits for Microsoft RC vulnerabilities have been found in the wild, haven't worked against IE11 on Windows 8.1, where CFG was present. So when you enable CFG, even though they found some vulnerabilities, they couldn't make the working exploits from the bad guy's side, actually. So you might wonder why CFG is so powerful, right? So CFG is really powerful because for a long time, actually, the bad guys abused this VF table corruption for a very, very long time. But CFG is just like cutting that very like well-known path, actually. So for example, when CFG was not present actually, so VF table corruption was like from the actual Flash exploit code, it is just 4 lines of code. And it is just reading from the first line, it's just reading some object address, and it is just overriding some one function pointer inside the VF table, and you will call one method from that object, the corrupted object. And from the yellow background line, actually it's just calling file reference cancel. And this one is very well known, like an exploitation target object. And after this, actually when the cancel method is called, actually the control flow will jump to shellcode. So the exploit is very, very concise and very, very effective. It works very well. But after CFG, all this like a small, like a very simple trick doesn't work anymore. So the thing is that after Adobe introduced CFG in 2015, so we observed very interesting techniques coming back, like something like MMGC, so abusing. So MMGC, you might have heard about this before, but from the actual document, actually this is MMGC is a kind of a long description, but MMGC is basically the memory manager for ABM2, which is used for Adobe Flash Player. And the attackers actually try to parse MMGC internal structures to find any interesting structures, object they want to corrupt. So the thing is that we observed full-blown object finder inside for MMGC. So the first in the wild CB 2016-1010 exploit actually showed very interesting technique. And it is actually parsing whole MMGC internal structures. So we are going to talk about it here, how they wrote it and how it works. So first stage is actually leaking some like a native memory out of some internal object. Starting from there, actually, I just summarized the whole process here, enumerate the fixed blocks. That is the function that actually can enumerate any memory blocks that has specific size. And if you look into the code, it is just calling parse fixed alloc header by size. So everything, the thing is that from the MMGC, the memories are aligned, linked by the sizes. So from this exploit, actually, parse fixed alloc header by size. So if you know the size of your target object, actually you can find it. But there can be multiple different objects with the same size. In that case, you can use some heuristics that are specific to the target object that you are looking for. So parse fixed alloc header by size will call locate fixed alloc editor by size. The code looks like this, but you don't need to try to understand it here. But some pre-defined some constant values are determined here. And here is a very interesting part here, right? So get size class index, it's a kind of the offset table that is used inside the exploit. And this same thing is actually almost same table. This table and this table, they are actually same. And this table is happening inside ABM Plus source code. So our suspicion is that they just studied ABM Plus source code and they just figured out how they can traverse MMGC memory space. From the exploit code itself, right? So get class on the left side, it is get size class index function from the exploit code. On the right side, it is the actual source code from MMGC, the ABM Plus source code, and actually they are same. And about the structures, actually the fixed alloc structure is defined from the ABM Plus source code like this. It has some linked list of fixed block. And it is from the exploit, actually, it is actually doing same thing. So the exploit code has even the symbols are same. M, first block, and those symbols are actually appears in the source code, and they are just using same symbols, symbol names here, and whole thing. So when everything is run, actually, when you call this parse fixed alloc header by size, then if you just pass some size of some specific object, then it will return the actual memory address of those fixed alloc structure. After that, the fixed alloc structure has linked list of fixed blocks, and it will go through those lists, and it will look for whatever interesting object out of those. So there can be multiple objects, but they can use various tricks to find the accurate object they are looking for. So the parse fixed block on the left side, it's the exploit, and on the right side, it is the source code from AVM Plus. And looks like they are just copy and pasted everything from there. So using this technique, actually, they can do a lot of various things. They can actually locate like a various internal objects, but they can also leak some object they created. And one of the techniques they are actually doing is that if they have byte array object, actually they can locate the exact virtual address of those raw data. So from here, get byte array address is used, and it is calling enumerate fixed blocks. So this enumerate fixed blocks that we just talked actually will return the linked list, the list array of these fixed blocks, and one of those should be the target object that it is looking for. And from here, actually, get byte array address function is using some search marker to find the accurate, the exact byte array object, actually, right? So when you create new byte array, you just put some random bytes there, and you go through each byte array object and look for those markers. If those markers are present from the actual virtual address space, then you know that this byte array object is what you are looking for. So the next technique that we observed was actually acquiring GC block structure. From the CB 2015 A446 actually exploit in the wild, actually it used memory predictability to locate MMGC related data structures. So this is one problem with the MMGC, because for this technique to work, actually it didn't spray that much of objects. So just like few megabytes of spraying actually made some object, some MMGC related internal object to be landed into some very specific memory address. So if you look into GC block header structure, actually, if the exploit is some heap spraying, actually, the specific address here, 0x1a 000000 is predictably allocated by GC block object. So the exploit knows that after some spraying, they know that, oh, if you read this address after you acquire RWM primitive, you can know that if you read this memory, then you can actually reading GC block header. And because from the AVM Plus source code, you know that it has some pointer to GC object, which has a lot of valuable information inside it, then it uses that address to go further. So that is the other technique we talked about. And MMGC itself is not exploited, right? So it's not actually doing any RCE or anything. But to actually run some code, you need more things to be done. So this is a very important slide, actually. So attack landscape changed to actually JIT recently. So everyone observed that, right? So the attackers are moving into JIT space. The conceptual attack actually was presented last year from Francisco Falcon. And it was like a JIT code was not actually CFG'd. So it doesn't have any CFG. So if you figure out some JIT code address, then you can just actually use JIT, some object inside the JIT to actually execute some code. But this technique was actually mitigated by introducing some runtime CFG code. But in the real world, actually, we saw that, for example, CB 2016 and 1010, or CB 2015 or A446, we observed more advanced attacks than the attack that presented from Francisco Falcon. And the technique is actually corrupting the return address of the G stack, but this one is actually a well-known limitation with CFG, because CFG is guarding against object corruption, but not G-stack corruption. And we are working on some solution upon this, and we are going to release a detailed analysis upon this attack later with further research. But today we are going to share some details upon some other very interesting techniques we observed, like a free list abuse method, and the other one is a method input GPR corruption method. Like as we talked, the byte array can be abused to read or write to some specific location, and you can acquire the actual address out of it. For example, CB 2016-1010, it will be calling some allocate byte arrays function to allocate the two buffers. And whenever you allocate some buffers using byte array object class from ActionScript, the default permission is actually RW. So even though you put some shellcode there, even though you redirect some control flow there, it will not execute anything because there is no executable bit set. But in this case, it uses a very interesting technique, and that is the free list override. And if you look into class GC heap, it has free list array. And if you override the prev and next the doubly linked list pointer values here, then actually you can assign your own memory as one of the free list member, right? Because it's a linked list, you over a prev and next member here, then you can make it to point to your own memory, which might be RW, it doesn't matter because it's the data structure there. But the thing is that when you override those field and make it to point to your own heap block structure, the first member of the structure is base address. And if you override, if you assign your own shellcode address to this base address, then it will be pointing to your own RW permissioned address, right? Then when actually GC heap alloc block is called, and it will go through some free list, and it will just find some free heap block from your own fake free list, and it will use it to actually allocate, recycle those memories. And the problem is that from the MMGC, originally when they recycle some pre-used memory, they don't clean up, and they just use whatever portion they want to use, but some garbage memories are still there. And as I talked, actually, we allocated some byte array already, which is pointed to by this fake heap block. And this address contains shellcode. This memory space contains shellcode. Not in the beginning, but in the middle. So the technique the attackers are using is they just create some event handler, just shown on the left. Do init delay, it's an event handler which is called like frequently, it's a timed event handler. So it will be just called like every second or something. And whenever this event handler, which is very short code, when this event handler is called, then the GC heap alloc block will actually try to allocate the JIT memory from this free list space. And it will just reuse the byte array we allocated before, and it will just change the permission bit to RX. So this is the technique they are actually using. They were using to actually achieve code execution. But this one is actually fixed. The fix is very obvious, right? So whenever you allocate a new JIT memory, you just clean up whole memory to 0 or something, then your shellcode will be gone. So you don't have any access to the shellcode and nothing will be executed. So the other JIT attack method we observed is actually using input GPR pointer corruption. So this pointer, this handler, actually callback is called when JIT method is returning. So whenever the JIT method returns, it will call end course method, and it will call this pointer value. So if you overwrite this pointer value to whatever shellcode you have, if you know the shellcode location, then the code execution will happen. The technique here they used is actually, they made their own custom byte array, and they just spray on the heap. And there are some assignment there to initialize some variable. Yeah, here is the actual corruption target method. It doesn't have anything inside it, it just returns 0. It's just blank method. And this blank method is actually the corruption target. And these 4 lines of Flash Hacker log actually shows how the exploit locates the actual method info input GPR. So I put some detailed explanation here. So the custom byte array is located at some specific memory. So in this case, we also see the memory location, address predictability. So you can like allocate some specific object as some specific location in predictable way. So that is one problem with the MMGC. And it will just go through some multiple structures and hop through those structures, and you will override input GPR pointer here. And the original input GPR pointer is pointing to some flash code originally, right? Just shown here. But after corruption, actually, it will be pointing to shellcode. And whenever you just call this dummy method, actually, when the dummy method returns, instead of calling some flash utility routine, it will just call shellcode. And the actual code that triggers shellcode is actually calling the dummy method. So these are very interesting techniques. These 2 are just JIT attack techniques that we presented here. And the next one is function object corruption technique. This one is also very interesting because we observed this from hacking team incident actually. And this method was reused again later by Domnium actor, which was targeting Southeast Asia. And the technique is kind of very straightforward here. There is some function object, and it has some internal call table for apply and call method. And there is also trigger, the dummy method here. So the dummy method and the exploit will try to corrupt the function table, virtual function table for this dummy method. And you see there's some address calculation here. And you will overwrite the apply or call method here. And for apply method, it will just overwrite to virtual protect API. And whenever you call virtual, the apply method upon this function object, then actually the virtual protect API will be called. This is the actual exploit code, actually. So I didn't do anything, but it's the actual decompiled code from the exploit. So if you look at each very well written, kind of organized code. So when actually the exploit works, if you go down to the native level, you can see the virtual, like the corrupted virtual function table, and it is calling the virtual protect here. And whenever it is doing shellcode execution, it uses call method here. So these things are very interesting because this kind of modularized approach it introduced actually makes writing shellcode robless. So there is no ROP or nothing involved, but the shellcode writing becomes just like something similar to what is that scripting actually. So if you look at the code actually, you can just pass the actual API you want to run, and you just pass the argument for that API, and it will just construct whole stack, and it will just run that specific API automatically. So this is very commercialized API exploit that we've seen ever, and it works like very efficiently actually. And whenever maybe the customer wants to, who bought this exploit wants to modify the exploit, it's very straightforward because it's not writing the native level like a shellcode or something. It's more about writing action script code. So just rewrite some action script code, and you have your own shellcode. So conclusion. So yeah, the thing is that even though we introduced some like different techniques here, right? So like decompilers, disassemblers, and even bytecode instrumentation technique, and native level debugging, even though you have some symbols or source code, ABM plus source code, it's not that easy to actually debug or reverse engineer these Flash exploits. And that's why not many actual informations are like a public maybe. But the approach you should have is like more combining different approaches, like not just decompiling, but you might rely on some decompiled code sometimes, but you can instrument some code, but instrumentation is not the silver bullet because it can break the exploit. So sometimes you instrument some code, but you need some low-level debugging too. And the ABM plus source code definitely helps because it has all those internal structures. And the other point is that recent exploits are focusing on MMGC. So the memory manager is the current target, and the memory manager is used to get access to JIT level because JIT is actually managed by the MMGC, right? So that is how they are now working on, the bad guys are working on right now. And the other point is that because a lot of important thing happens inside JIT level, even though you have symbols for example, for Flash, it doesn't help because everything happens in JIT level, and you need to match between the action script code, byte level code, and JIT level code. It's not easy to match in between them. So something is happening inside the JIT level, but it's just x86 or those assembly code, but you need to figure out how those are related to byte code level. So in that case, the byte code instrumentation helps a lot because you can put some helper function into some specific method you are interested in. Then you can use that as a kind of trigger or marker to debug into the native level code. And the last one is the predictability of heap layout from MMGC can be a problem because we saw a lot of exploits are using this, and you don't even need like a few gigabytes of heap spraying, but just like just few megabytes of heap spraying actually makes this condition happens. So those things are the conclusions, and we share the sample code that we used. Probably you can find it from somewhere here. And for every CV numbers and the exploit code, The techniques are actually shared here. So if you want to actually study these cases, you can do it yourself. And acknowledgement, actually, special thanks to Matt Miller, David Weston, Elia Floria for their support for this research. And that's it for the presentation, and let's have some questions if you have any. So we have exactly 5 minutes, so questions. You should have some questions. Yeah. You can like.
Can you hear me?
Yeah, yeah.
So is this a Microsoft project, or is this something that you're in particular?
This is Microsoft project actually. So we are working together with Adobe Security to improve Adobe Flash actually. So in the case, this information on the actual in the wild exploits are very, very valuable.
Mm-hmm.
Yeah.
Okay, thank you.
Any other questions?
Hi. You mentioned earlier, you mentioned something about CFG protecting diminishing the effectiveness of remote code execution, right? What's the cost and efficiency after the implementation of CFG?
I don't have actual numbers. There should be something out there, I guess, but because it's just few lines of assembly code, I don't think it's really that degrading any performance. So that is a question, right?
Thank you.
Yeah, thank you. Any others? We have 4 minutes. So, and I think that's it. And thank you.